In this lecture, we're going to present a simplified overview of tensors and their order. Let's consider R3 and let's equip it with an orthonormal basis set with vectors E1, E2, and E3. A vector U can be represented in component form as having three components U1, E2, and U3 under this orthonormal basis set. A tensor M as a linear map between R3 and R3 can be represented in component form or matrix form as having 9 components M sub ij. Now let's consider the same space with a different orthonormal basis set, vectors E'1, E'2, and E'3. From what we have studied previously, we know that to switch the components from this orthonormal basis set to this orthonormal basis set, we need this matrix of component Q sub ij, which are composed of the components of E'(i) dot ej. In the new basis set, U prime will have new components that are related to the original components using the matrix operation QU. Similarly, as we studied before, the new components of the matrix M prime, will have the components M prime sub ij. These components can be obtained using the matrix operation Q transpose. The fact that the components of U have one subscript and change according to this relationship, while the components of M have two subscripts I and j and change by the relationship QMQ transpose, have motivated the terminology first order tensors for U and second order tensors for M. Third and fourth order tensors can be envisioned that way, as linear maps that have 3 or 4 subscripts, as will be shown in the next few slides. Let's consider a linear map that takes matrices and gives you vectors. When applied to matrices, it will need 2 subscripts because the matrices have 2 subscripts, and because it provides a vector, it has another subscript. So, given an orthonormal basis set B with E1, E2, and E3, D would have 3 by 3 by 3 components, 27 independent components. Given an arbitrary matrix M, the vector arising from the application of D on M has 3 components. Each component is obtained by multiplying the respective components of D with the respective components of M. So U1 is equal to the sum of the respective components of D multiplied by the respective components of M. We will now investigate how the components of D, namely D sub ijk, change when a new orthonormal basis set B prime is used. The new components D prime ijk will be equal to the sum of summing over Lmn from 1 to 3, Qil, Qjm, Qkn, D sub Lmn. To find this relationship, we're going to follow a similar procedure to how we found the previous relationship early in the course when we talked about the change of the basis set. So, to show this relationship, we're going to write U, which is the result of applying D to the matrix M, and U prime, which is the result of applying D prime, which is D but the new coordinates of D, applied to M prime. We also know that U prime, because it's a simple change of basis, it's a vector, it's equal to Q multiplied by U. And U is equal to D applied to M. And M, because of the change of coordinates, is related to M prime with the relationship Q transpose M prime Q. If we take U prime from here and U prime from here, these two components are these two forms should be equal, and if we write them in component form, this component form it's basically D prime applied to M prime, so D prime ijk applied to M prime jk, where we are summing over from jk equal 1 to 3. On the other side, if we write this in component form, Q multiplied by D, and D is applied to this matrix. If we write this in component form, we're going to get this form. Since M prime is arbitrary, we'll find that this D prime ijk will have to be equal to the sum Lmn equal 1 to 3 of these components, which is the desired form. Let's now look at a linear map that has 4 subscripts. As an example, we can consider a linear map that maps second-order tensors, matrices, to second-order tensors, matrices. This is called a fourth-order tensor. Given a particular orthonormal basis set, C has 3 by 3 by 3 by 3 components. 81 independent components. And given an arbitrary matrix M, when we apply C to this M, we get a new matrix N. The components of N can be obtained by multiplying the respective components of C multiplied by the respective components of M. The new components of C, when we change from the original orthonormal basis set to the new orthonormal basis set, can be found using this form. C prime sub ijkl is equal to the summation qil qjm qkn qlo multiplied by clmno. Again, to show this, we are going to follow the procedures similar to what we presented earlier. Given an arbitrary vector M, N is equal to C applied to M. We also have that in the new components, N prime is equal to C prime applied to M prime. We are looking to find the relationship between C prime and C. To find the relationship between C prime and C, we're going to replace, we're going to first use the relationship between N prime and N. The relationship between N prime and N is given by Q and Q transpose. And N is equal to C applied to M. And because M prime appears here, I'm going to replace M with M prime. So instead of M, I'm going to apply Q transpose M prime Q. And so now comparing this form to this form and noticing that M prime is the same, I can now show the relationship between C prime and C. And if you write this in component form, similar to what we have done in the previous previously in this lecture, you'll find you'll be able to show this relationship, which is the desired form for the change of coordinates of a fourth order tensor.